In this module 2, we will learn about the qualitative behavior of the differential equation. We will start with the linear part of the differential equation. From there, we will conclude about the behavior of the linear part of the differential equation. Next, whether the conclusion holds true for the nonlinear part also, that is what we will check here. We consider the linear system dx dt is equal to ax plus by and dy dt is equal to cx plus dy, which we name as equation number 1. Here a, b, c, d are constants and real constants. Clearly, the origin 0, 0 is the critical point of 1, and we have to assume that the determinant a, b, c, d, which is equal to ad minus bc, not equal to 0. And hence we conclude that 0, 0 is the only critical point of 1. Let us assume that x equal to a e to the power lambda t and y equal to b e to the power lambda t be a solution of the linear system 1. And if we substitute those solutions, we will get the characteristic equation in the form lambda square minus a plus d into lambda plus ad minus bc is equal to 0. Let lambda 1 and lambda 2 be the two roots of the characteristic equation 3, and then we have to conclude what kind of behavior this differential equation portray for various values of the eigenvalues, and we have the following 5 cases. It may happen that the lambda 1 and lambda 2 are real, unequal and of the same sign, or lambda 1 and lambda 2 are real, unequal and of the opposite sign, or lambda 1 and lambda 2 are real and equal, or there may not exist any real value of lambda 1 and lambda 2. So, lambda 1 and lambda 2 may be conjugate complex, but not purely imaginary, and at the end lambda 1 and lambda 2 are purely imaginary. So, we have to consider all these 5 cases, and we have to conclude what kind of behavior or what kind of phase diagram we will get when we have this kind of eigenvalues. We put the behavior in the form of a theorem where we say that for the differential system 1, if lambda 1 and lambda 2 be the eigenvalues, then the behavior of its orbits near the critical point are the following. So, if lambda 1 and lambda 2 are real, distinct and negative, then we get a stable node. If lambda 1 and lambda 2 are real, distinct and positive, then we get an unstable node. If lambda 1 and lambda 2 are real, distinct and are of opposite sign, we get a saddle point. If lambda 1 and lambda 2 are real, equal and negative, we get a stable node. If lambda 1 and lambda 2 are real, equal and positive, we get an unstable node. If lambda 1 and lambda 2 are purely imaginary, we get a stable center. If lambda 1 and lambda 2 are complex conjugates with negative real part, then we get a stable focus. And if lambda 1 lambda 2 are complex conjugates with positive real part, then we get an unstable focus. So, summing up this theorem, you have to remember, if your eigenvalues are real and negative, you get a stable node, and in this case the stability is asymptotically stable. If your eigenvalues are real and of opposite sign, you get a saddle point which is definitely unstable. And if you get a complex conjugate, if the real part is negative, then you get a stable focus or stable chiral point, which is actually asymptotically stable, and if it is a positive real part, then it is an unstable. And if the eigenvalues are purely imaginary, you get a stable center. Now, let us take various examples so that this theorem is much clearer. In this example 1, we have to draw the phase portrait for the linear system dx1 dt is equal to minus 3x1 plus x2, dx2 dt is equal to x1 minus 3x2. Now, first we find the eigenvalues of this system. Now, 0, 0 is the only critical point of the given linear system because the determinant minus 3, 1, 1 minus 3 which is equal to 8 is non-zero. Now, the characteristic equation of this differential equation is given by minus 3 minus lambda 1, 1 minus 3 minus lambda is equal to 0, and this can be easily expanded and solved for lambda values, and two values of lambda, namely lambda 1 and lambda 2 are respectively minus 2 and minus 4 respectively. So, as you see that both the eigenvalues are real and negative, and hence from the previous theorem we conclude that the critical point 0, 0 of the given system is a node and it is asymptotically stable. Now, let us look how this node will look. So, what you see here is the diagram of a stable node where all the paths will approach the point 0, 0 and ultimately will also enter the point 0, 0, and hence it is asymptotically stable. In our second example, we consider the linear system dx1 dt is equal to x1 and dx2 dt is equal to minus x2. So, the very first thing which you do is to find this determinant 1 0 0 minus 1 which you get from here, because you can write this as x1 plus 0 dot x2 and this as 0 dot x1 minus x2, and please check whether this particular determinant is 0 or non-zero, and if it is non-zero then 0, 0 is the only critical point of this linear system, and to get this point all you have to do is put this right hand side equal to 0 and this right hand side is equal to 0. Once you get the critical point, you find the characteristic equation given by determinant of a minus lambda I is equal to 0, and if you do that you will get this particular equation which is 1 minus lambda 0 0 minus 1 minus lambda is equal to 0, and solving this equation we will get lambda 1 is equal to 1 and lambda 2 is equal to minus 1. Thus, we have two eigenvalues which are real but are opposite signs, and hence from the previous theorem we conclude that the critical point 0, 0 of the given system is a saddle point and it is unstable. So, this is the phase portrait of the saddle point where you have two half lines which is entering 0, 0 in the opposite directions and two half lines which is moving away from 0, 0 in the opposite directions. So, this is the part which happens when t tends to plus infinity, and this is the part which happens when t tends to minus infinity. To get the non-linear, non-rectilinear paths, we have to consider the asymptotic towards these two lines, and the direction of this curve will depend on the direction on these lines. That is, this path is coming in this particular direction and then in this particular direction. Hence, the paths which is asymptotic will be from this direction towards this direction, from this direction towards this direction. The same thing is followed all over this graph, that this non-rectilinear path will follow from this direction to this direction, because this line has come from this direction and then moves towards this direction. In our next example 3, we consider the linear differential equation dx1 dt is equal to x1 and dx2 dt is equal to x2. Again, in this particular case, 0 0 is the only critical point of the linear system, because 1 0 0 1, which is equal to 1, is non-zero. The characteristic equation of this given differential equation is given by mod of a minus lambda I is equal to 0, which is 1 minus lambda 0 0 1 minus lambda, and we get the two values of the eigenvalues as 1 1. Therefore, we have the eigenvalues which are real, equal and positive, and from the previous theorem we conclude that the critical point 0 0 of the given system is a node and it is unstable. If you now look into the figure, all the arrows, they are moving away from the origin, that is away from the critical point 0 0. So, this is the phase portrait of the unstable node as t tends to minus infinity. In our next example, we have to find the phase portrait for the linear system dx1 dt is equal to x2 and dx2 dt is equal to minus 4 x1. Now, 0 0 is the only critical point of the given linear system, because the determinant 0 1 minus 4 0 is equal to 4, which is not equal to 0. Now, to obtain this, you have to write this differential equation in the form dx1 dt is equal to 0 dot x1 plus x2 and dx2 dt is equal to minus 4 x1 plus 0 dot x2. And if you do that, you will get this particular determinant. As before, the characteristic equation of the given differential equation is given by determinant a minus lambda I is equal to 0, which is 0 minus lambda 1 minus 4 0 minus lambda equal to 0, which gives lambda 1 equal to 2i and lambda 2 is equal to minus 2i. Thus, both the eigenvalues are purely imaginary and the critical point 0 0 of the given system is a center and it is stable. Now, if you look into the phase portrait, it will look something like this, where all these are closed paths, not necessarily circular in nature. They can be elliptic in nature or they can be any closed path, which must contain this 0 0. And as t tends to plus infinity, the diameter will approach the point 0 0 and ultimately will coincide with 0 0. Please note, in this case none of the path will pass through this point 0 0. In our next example, we have to draw the phase portrait of the linear system dx1 dt is equal to x1 plus x2, dx2 dt is equal to minus x1 plus x2. As before, we check that 0 0 is the only critical point of the given linear system, because the determinant which is obtained from the coefficients of x1 and x2 given by 1 1 minus 1 1 is equal to 2, which is non-zero. The characteristic equation is defined as determinant of a minus lambda I is equal to 0 and is given by 1 minus lambda 1 minus 1 1 minus lambda equal to 0. And if you solve this characteristic equation, we will get lambda 1 is equal to 1 plus I and lambda 2 is equal to 1 minus I. So, the eigenvalues are complex conjugates with positive real part, and hence from the previous theorem we conclude that the critical point 0 0 of the given system is a spiral point or focus and it is unstable. If you now look into the phase portrait of the unstable spiral point, it will look something like this. And as you see, these paths, they approach the point 0 0 in a winding like manner, but will never enter the point 0 0, and since it is unstable, the arrows are moving away from the origin. We have learned about the qualitative behavior of the linear differential equation, where we have taken only two differential equations. We have seen the cases where, depending on the eigenvalues, whether the system is a node, is a stable focus, is a center, or is a saddle point. Now, all these we have considered about the linear case only. Next, we will look into the system where we have to consider the nonlinear part. Whether the phase portrait remains the same is that what we are going to find out in the case of nonlinear systems. We now look into the stability of the nonlinear systems. We consider the nonlinear system of the form dx dt is equal to ax plus by plus p1 xy, and dy dt is equal to cx plus dy plus q1 xy, given by equation 9, where here a, b, c, d's are real constants and p1 and q1 are the nonlinear part of the given differential equation. And we assume that they will satisfy the following properties. Number 1, a, b, c, d are real constants and determinant a, b, c, d is not equal to 0. And number 2, p1 and q1, which are the nonlinear part of the given differential equation, have continuous first partial derivatives for all xy and are such that limit xy tends to 0 0, p1 divided by square root of x square plus y square is 0. Also, limit xy tends to 0 0, q1 divided by root of x square plus y square is 0. So, basically what we are finding out here is, given a nonlinear system, whether the same kind of theorems they hold for the linear system is also true in this case or not. If yes, then what are the deviations we will be seeing? From the nonlinear system, we get the corresponding linear system as dx dt is equal to ax plus by and dy dt is equal to cx plus dy, which we get from equation 9 by neglecting the nonlinear terms p1 xy and q1 xy. It can be easily seen that both the system have an isolated critical point 0 0, and let lambda 1 and lambda 2 be the roots of the characteristic equation lambda square minus a plus d into lambda plus ad minus bc is equal to 0 of the linear system 10. So, what we are going to do here is, we will put all these results in the form of a theorem, where we will see that depending on the roots on the eigenvalues of the characteristic equation, the behavior which it shows in case of the linear system, is it true for the case of nonlinear system or not. Please note, our nonlinear system in this case is referred as equation 9 and our linear system is referred as equation 10. So, in the next theorem, we will refer equation 9 and equation 10 frequently, where you have to understood that when we mention 10, it is the linear system, and when we mention 9, it is the nonlinear system. So, the conclusion is, the critical point 0 0 of the nonlinear system 9 is of the same type as of the linear system 10 in the following cases, which means that whatever behavior the linear system will show is also true for the nonlinear system in the following cases. So, the first one is if lambda 1 and lambda 2 are real, unequal and of the same sign, then not only 0 0 is a node of the linear system 10, but also 0 0 is a node of the nonlinear system 9. If they are of same sign, that is negative, then it is a stable node, and if they are of same sign and positive, then it is an unstable node. If lambda 1 and lambda 2 are real, unequal and of the opposite sign, then not only 0 0 is a saddle point of the linear system 10, but also 0 0 is a saddle point of the nonlinear system 9. The third point, if lambda 1 and lambda 2 are real and equal and the system 10 is not such that A is equal to D not equal to 0 and B equal to C equal to 0, then not only 0 0 is a node of the linear system 10, but 0 0 is also a node of the nonlinear system 9. Please note, here it is given that the system 10 is not such that A is equal to D not equal to 0, B equal to C equal to 0, and this means that the system does not satisfy these two conditions, that is A equal to D not equal to 0 and B equal to C equal to 0. And the final point, if lambda 1 and lambda 2 are complex conjugates with non-zero real part, then not only 0 0 is a spiral point of the linear system 10, but also 0 0 is a spiral point of the nonlinear system 9. And if the real part is negative, then we get a stable focus or stable spiral point, and if the real part is positive, then we get an unstable focus. Summing up, here you have to memorize that if lambda 1 and lambda 2 they are real, unequal and of the same sign, then it is a node for both the cases. If they are real, unequal and of opposite sign, then it is a saddle point for both the cases. And if it is a complex conjugate where the real part is non-zero, then it is a spiral point for both the cases. Now, here where there is will be some deviations. The critical point 0 0 of the nonlinear system 9 is not necessarily of the same type as that of the linear system 10 in the following cases. So, in first case, if lambda 1 and lambda 2 are real and equal and the system 10, which is the linear system, is such that A equal to D not equal to 0 and B equal to C equal to 0, then we conclude that though 0 0 is a node of the nonlinear system 10, the point 0 0 may either be a node or a spiral point of the nonlinear system 9. Please note, in this case it is given that it has to follow that A equal to D not equal to 0 and B equal to C equal to 0. In the second case, if lambda 1 and lambda 2 are purely imaginary, then though 0 0 is a center of the linear system 10, the point 0 0 may either be a center or a spiral point of the nonlinear system 9. We now take an example which will be clearly explain the theorems which we just stated. So, in this nonlinear system given by equation 12, which is dx dt is equal to 8x minus y square and dy dt is equal to minus 6y plus 6x square, we have to determine the type and the stability of the critical point. From the nonlinear system 12, we consider the linear system by neglecting the nonlinear part minus y square and plus 6x square, and we get the system as shown in equation 13 as dx dt is equal to 8x and dy dt is equal to minus 6y. The characteristic equation of this linear system is lambda square minus 2 lambda minus 48 is equal to 0, whose roots are 8 and minus 6. Therefore, the roots are real, unequal and of opposite sign, and hence we conclude that the critical point 0, 0 of the linear system is a saddle point. Now, to obtain a conclusion for the nonlinear system, we first have to see that the following two properties are satisfied. The very first one is a, b, c, d determinant of that is not equal to 0, and in this particular case a is 8, b is 0, c is 0 and c is minus 6, which is clearly minus 48 and non-zero. And next you have to prove that P1 and Q1 have continuous first partial derivatives for all x y. It can be easily seen that both P1 and Q1 are algebraic function, and hence they will be continuous first partial derivatives for all x y. And also you have to prove that limit x y tends to 0, 0 minus y square by root of x square plus y square is equal to 0. Also limit x y tends to 0, 0 6x square divided by x square plus y square is also equal to 0. Now, here we prove that limit x y tends to 0, 0 6x square divided by x square plus y square is equal to 0. We use the delta epsilon definition to prove the value of this limit. So, in the format that given any epsilon positive, there exists a delta positive such that mod of the function f x y, which is in this case 6x square divided by root of x square plus y square minus 0 as the limit is 0, is equal to mod of 6 r cos square theta, and this we get by putting x equal to r cos theta and y equal to r sin theta in this particular expression, and clearly square root of x square plus y square is going to give you r square, which comes out of the radical sign to give r, and which cancels with the numerator to give you mod of 6 r cos square theta, and which is less or equal to 6 r because cos theta is bounded. And this r can be written as square root of x square plus y square, and which is less than epsilon whenever mod x is less than delta, mod y is less than delta, where delta equal to epsilon by 6 root 2. Please note that this kind of problem we always put x equal to r cos theta and y equal to r sin theta, as it is very easy to handle. Now, once you get this right hand side as a function of r, it is very easy to replace this r by square root of x square plus y square, and basically here you get a circle x square plus y square is equal to epsilon square by 36, and you choose your delta in such a manner that the sum of x square plus y square gives you epsilon square by 36, and that is the trick of this problem. And once you prove that these two properties, then we conclude that the critical point 0, 0 of the nonlinear system 12 is also a saddle point and it is unstable. In this module, we have learned about the qualitative behavior of the linear system of differential equation as well as the nonlinear system. We have seen that if we satisfy two properties, then the conclusion that we get of the linear system also hold true for the nonlinear system, except for few cases. In our next module, we will see why the qualitative behavior of the system is a node or is a focal point or is a saddle point based on the mathematical proofs. Thank you.